I'm Tim Ventura from AmericanAntiGravity.com, and I'm speaking with Dr. Lisa Randall, Professor of Theoretical Physics at Harvard University. Dr. Randall is the winner of numerous scientific awards and has held professorships at both MIT and Princeton, in addition to her current position at Harvard. She's also one of the world's leading experts in string and brane theory, and she's agreed to share her insights with us into this remarkable emerging branch of theoretical physics. Well, let's start out with an overview of brane theory. Like most people, I felt very confused about this topic until seeing an overview of your research on a Science Channel special that really described it for the layperson. Now, in all honesty, despite my respect for Brian Greene's work, your explanation made a lot more sense. And I'm wondering if it's correct that you're suggesting the universe we live in is created by kind of an overlap of what are basically field membranes.
Well, we don't talk yet so much about the creation of the universe because that's just a tough question that no one really has a right to answer at this point. We just don't understand physical processes at that scale. But what we do suggest is that today we could be living on a brane that exists in a higher dimensional space. So let me backtrack a little bit. So what is a brane? A brane is a lower dimensional space that sits inside the higher dimensional space. And it could be that all the stuff that we're made of, quarks and leptons, particles, galaxies, that are our universe, could all be stuck on a brane, even though there are extra dimensions. So, for example, if that brane has three spatial dimensions, if the brane extends through three dimensions of space, even if there are many more dimensions, we would be stuck on the brane. We wouldn't experience it. However, gravity would experience the extra dimensions, and so we could communicate in principle with those extra dimensions, and they can communicate with us. And that's what makes these theories so interesting. What would it be like if we were on a brane, but gravity surrounding us is actually gravity of higher dimensional space?
Now, you've just published a book on brane theory entitled Warped Passages. And for people in the audience who'd like to learn more about this really is kind of the must-read book of the year for string and brane theory. Could you tell us a little bit about the book?
Sure. So the book isn't just about branes. It's called Warp Passages: Unraveling the Mysteries of the Universe's Hidden Dimensions. And when I talk about hidden dimensions, I'm talking about real physical space-time dimensions, but all the other things that we've discovered in physics in the last 100 years or so. So in order to explain why we're so interested in brane theory today, why we think these might be relevant to our world, one really wants to understand some of the background too. Probably some of your listeners already know a lot of this, but I start by first just talking about extra dimensions and branes quite generally, what they are. But then I go on and really just give the basics. I start with quantum mechanics and relativity, and then I describe where we are with particle physics. There's not many good reviews on where we are with particle physics, what we understand, what we hope to understand from collider experiments. But also with the ideas I'm talking about, of course, tie in with string theory as well. So that's sort of a different track, sort of dealing with a theoretical puzzle about the incompatibility of quantum mechanics and gravity at very tiny scales. And so I've introduced string theory and say where branes play a role in string theory. And then it all ties together in a lot of it is about my recent work, but I talk about other people's work too, who've worked on extra dimensions and branes in particular, in extra dimensions.
Sure.
So it covers quite a lot, but it's sometimes I wondered, is it too much? And I think for some people it's a lot, but I've gotten so many emails from people saying how they really appreciate it and how they've read a lot of physics books and then finally they can all see how it fits together. It's really nice when I get those. I feel like it was worth it.
Absolutely. Well, I think one of the real values of books like this, Warp Passages in particular, is that physics is so fragmented now in terms of what people see on the news. They may see one breakthrough in one place but not another.
That's so accurate. And that's right. And so, you get the sort of gee whiz version or the sort of mystical, magical version, but you don't actually see, why do we believe these things? Or why do we think they're worth studying even if we're not sure they're right? And so what are our motivations? I like puzzles and games. That's the kind of thing that would draw me in. And a lot of the time when you hear stuff, it's just people telling you things. And I really wanted to give a complete enough picture that people could really be drawn into it.
Absolutely. Well, now, I saw a description portraying two membranes in space, and I think this was on the TV show. And now, one of these, as it was described, contains the gravitational force, and then the other was said to contain the strong, weak, and electromagnetic forces. The idea, I guess, was that they collided, but as I understand things, you don't totally support that.
Well, you're sort of combining together two theories there, I believe. So you started off actually talking about a theory related to some work I did, and then you sort of merged into some other work. So the idea of the colliding branes, I mean, yes, they might have collided, but we just can't calculate. Once those branes get too close together, we don't know what happens. So we have a picture, that is to say, I developed a picture with my collaborator Raman Sundram, which is actually at least as intriguing. So we have two branes in this picture. And it's not that gravity is strictly speaking on one brane. After all, gravity, higher dimensional gravity, is connected to the entire geometry of space-time. But nonetheless, what we find is that gravity that looks as if it is four-dimensional gravity, that is to say, it obeys Newton's law, for example, you find it heavily concentrated on one brane, very weak on another. So what we have is one brane where gravity is concentrated, another brane on which we live, and therefore all the forces we experience live, such as the strong, weak, and electromagnetic force. Now, we experience gravity too, but it's extremely weak. But that's exactly what we want. So in this theory, the cosmology is actually quite intriguing. In the early universe, you basically have one brane, but as the temperature cools, you have a phase transition, and the second brane would form, and that would be the brane on which we would end up.
Now, one of the problematic issues with this for me had been, and I guess, not so bad with radio, but definitely for TV, they had a portrayal of this on the show showing the different branes, and I was looking at it and yet realizing that this is a three-dimensional portrayal of something that doesn't occur in 3 dimensions. It results in 3 dimensions. So, I don't know, have you ever had issues describing it, I guess, in those terms?
Well, I mean, that's one of the things that we as physicists do. We kind of go back and forth between higher dimensional description and what we call four-dimensional description when we include time. Because after all, things do look as if they're four-dimensional, so there should be some description which, is approximated by a four-dimensional world. But then you can ask, where does it deviate? So you can look at it from a higher dimensional perspective, but sometimes it's useful to look at it from a lower dimensional perspective. It's sort of making an approximation in some sense. When you're in a limit where you don't see the extra dimensions, you can sort of treat it as lower dimensional, even though ultimately it is higher dimensional. So to really understand what's going on, you generally want to be in the higher dimensional world.
Sure. Well, I guess one of the things that I'd like to address is why gravity is so weak compared to the other forces. It almost seems like a van der Waals force, doesn't it?
Well, it is much, much weaker than you would think. It's not like a van der Waals force because it has a different dependence on separation with distance. So we know what the dependence is on separation. And it's actually 1 over r squared, just like for electromagnetism. But the bizarre thing is that it's so much weaker. Now, of course, gravity doesn't really seem very weak. But, of course, when electromagnetism competes with gravity all the time, you see it when you see a magnet pick up a paperclip, but you see it all the time. And if you looked at particles, elementary particles, gravity is just completely negligible compared to electromagnetism or the weak or strong nuclear forces. So we know that gravity is just much weaker, many orders of magnitude weaker than the other forces we know about, and the question is why. And that's where the warped of my title comes in, because it turns out in a higher dimensional geometry, basically the one I was describing earlier, where gravity is concentrated on one brane, but we and the strong, weak, and electromagnetic forces are on the other, what you find is that space-time is so warped, geometry is so warped, that where we are, gravity is exponentially weaker than you would expect. So now I can explain many orders of magnitude really simply. I'm just not where gravity is concentrated. Even a fairly modest distance away, you would see gravity as much weaker than the other forces.
But would that suggest that there was almost kind of another dimension where gravity was the predominant force then?
There could be another region of, say, the 5th spatial dimension. We only need one extra dimension for this to work. And if there's one spatial dimension, there would be another region where gravity is comparably strong to the other forces, should they exist on the other brane. You have to ask what the forces are there. It could be that they experience the same strong, weak, and electromagnetic forces we do. They could actually experience different forces that live just on their brane. But gravity would be stronger in other places. That's absolutely right.
Now, one of the things that I was hoping to address, and I guess this has kind of been one of the challenges for string and brane theory, has been testability. As I understand the situation, these models can predict phenomena that we currently understand, but there's been some difficulty in designing an experiment to validate these models specifically. Could you comment at all on that?
Well, again, the models that explain the weakness of gravity, no matter what explains the weakness of gravity, is really interesting. And the reason it's so interesting is because we're going to test them. In particular, if this theory, this warp geometry I told you, is right and actually produces what we know as what we call the hierarchy, the reason gravity is so weak, it actually will have testable consequences at a collider called the Large Hadron Collider, the LHC, that's going to begin operation in 2 years, so pretty soon. And what that is it's a big accelerator. It will be located near Geneva in Switzerland, and it's 27 kilometers in circumference. And so they're going to accelerate protons by having them go around this enormous ring and then collide them together. And through Einstein's famous relation, E equals mc squared, you can produce heavy particles. And in this case, the hope is that you would produce heavy particles that are heavy because they travel in the extra dimensions. The fact that they travel in extra dimensions gives them extra energy, which we would see as extra mass. So there would be new heavy particles, partners of the graviton being the particle that communicates gravity. There could be these new heavy partners of the graviton. We call them Kaluza-Klein modes after the physicists who first started thinking about extra dimensions. And those could actually appear in collider experiments, and that would be extremely exciting. It would really be evidence that this theory is right.
It would be. That would be truly amazing. Well, on the subject of dimensions, IBM recently unveiled a 5-bit quantum computer that they claim validates the many worlds interpretation of quantum mechanics. And one of the things that struck me was that in contrasting these models, it appears that Brane theory contains kind of a geometric description of dimensions separated by the fundamental forces, whereas the quantum mechanics model may contain an infinite number of dimensions containing all of the fundamental forces. Do you have any thoughts on reconciling the difference in these models, or is it too implicitly tied to the models themselves?
Well, I think the key is the word you used when you first described the IBM machine. You said interpretation of quantum mechanics. We actually know how quantum mechanics works. We know how it predicts things. And the question is just if you want to try to interpret it in classical terms. I don't feel any need to interpret it in classical terms, but when you do, you're led into all these, it's really just explanation. It's really just metaphor. I don't know that really exists. It's just a way of interpreting what you see. So those dimensions, they are not real physical dimensions. What we're talking about are real physical extra dimensions of space, really places that things could move, things that it's the space-time that's connected to gravity. See, that's those dimensions that you have on that IBM machine. They have nothing to do with gravity, but we know that space-time is connected to gravity. So those are the kind of dimensions I'm talking about.
Oh, so the metaphor really does come into play, and probably is just kind of a human explanation for things that we have a difficulty grasping, I guess.
I think that's right. I think it's just trying to make people happy about. See, if we had existed on atomic scales, if we just were atoms, we wouldn't be unhappy about quantum mechanics at all. That would be our fundamental rule. It's the fact that we see things classically, and then we tie ourselves into not trying to interpret quantum mechanics in classical terms. Really, what you should be doing is interpreting what you see, classical things, from quantum. Quantum physics leads to classical predictions on the scales we see. But you can't get quantum mechanics from classical physics, and that's what people keep trying to do.
Sure. Well, I guess I should preface this question a bit beforehand, because this helps reconcile, I guess, my own end of things in terms of there really being two types of gravity modification research. The first is mainstream work being done by, well-reputed, credible scientists into concepts like high-frequency gravity waves, and then the other is the controversial, culturally entrenched concepts that originate from engineering, folklore, and science fiction. Now, we've tried to really cover both on American Anti-Gravity, which really kind of makes life anything but dull. But I guess, that being said, do you think that string or Brane theory is ever going to provide us with maybe that first type, the more credible approach to a theoretical leverage into manipulating gravity?
Well, I don't know how far we're going to get in terms of having huge amounts of energy involved, but I think we could conceivably learn things about gravity waves and what gravity wave signal might mean. After all, if there are these extra dimensions, it could be that our only gateway into those dimensions really is gravity. We'd really have to be able to communicate via gravity. So I think as gravity wave detectors advance, we might have more ways of communicating with those extra dimensions. In terms of manipulating the dimensions, I have a friend that always asks me to do that. but I don't think that we can do that. We certainly don't know any way to do it now. So I could tell you that we might, but my guess is as good as anyone's at this point. We're really far from that right now.
Nonetheless, it's great feedback. It's been one of the popular questions: is will string theory, will brane theory play a role? So it's good to hear your thoughts on it. Now, I
guess
to
think about, but right now I don't know how we would do it.
Well, one of the precursors, or at least according to Michio Kaku, to string theory, was Einstein's unified field theory. And I did a story on this last year, and I picked up a bunch of interesting tidbits from actually a couple of pretty interesting scientists in the process. One of the things they talked about was the concept of teleparallelism, and they were also talking about torsion effects to allow something almost like macro-scale quantum tunneling, or perhaps something like the subspace drive that we see in Star Trek. Now, I guess the idea, in the simplistic term, almost relates to that old idea of folding a sheet of paper in half to make two distant points in space overlap. And I'm wondering if you have any thoughts on string or brane theory, or perhaps torsion effects to achieve this.
So you just covered a lot of ground there. You covered unified theory, these torsion effects, and I think you had something else at the end. Oh, that's right, folding a sheet of paper. So let's think about them all in turn, or perhaps together. The first thing I want to be clear on is that I am really, really careful in my book to distinguish what we know through physics from what is fiction, or what are things we're working on, what are things we'd like to answer.
Sure,
especially when you're talking about subjects as sort of exotic as extra dimensions of space and brane theory. It's so easy to confuse fiction and fact. And really, I thought one of my responsibilities as a physicist who actually knows what's going on was to really make sure people get the truth. I didn't want to say, oh, we can do all these fancy torsion things that we really don't know about. You can speculate and say, things can happen at a wormhole, but all of those regions deal with quantum gravity, and that is to say, regions where we have to really have the theory, like string theory, that we understand well enough to predict things taking into account quantum mechanics and gravity. And on the whole, we don't have that yet. So your guess is as good as mine. It would just, at that point, it's fiction. It's stuff that we think could happen, but we just don't know if it does happen. So I'm trying to concentrate on stuff that I think does happen, and some pretty interesting things do happen. This weakness of gravity, this warp geometry, this warp space-time. Another really exciting thing about this warp geometry that I told you about that might explain the weakness of gravity is that you can actually get grand unification in this theory. You can get the unification of all the forces. That is to say, at high energies, it could look like there's a single force, even though we experience different forces at low energies. So it might actually be a route to a unified theory as well. So there's a lot of exciting things that could happen.
Absolutely. Well, and it seems like this is kind of yet another signpost on the path to greater understanding of physics also. And hopefully an emerging theory like this will continue to develop and someday may even show those cross-linkages.
Well, it's really true. I mean, one of the things that we found by studying this sort of new context, these extra dimensions with branes, we've really discovered things that have eluded people that really worked exclusively on gravity, because we were asking different sorts of questions. We were coming at it from a different angle. One of the really exciting things we found is that because space-time can be so warped, you can actually have infinite extra dimensions of space that we don't see. Since in the 1920s, people thought that if there were extra dimensions, they had to be tiny, so tiny we couldn't see them. But what we find is because of this concentration of gravity that occurs when space-time is warped, you can actually get away with infinite extra dimensions. It's really remarkable. So no matter what, we are definitely learning new things about just the equations that we know about, Einstein's general relativity. This is stuff we understand, and we are finding new solutions. It's really exciting.
Absolutely. Well, one of the things that I also like to touch on is on the subject of quantum mechanics is the fact that a lot of, well, maybe just the engineering community, but a lot of people seem to be becoming disenchanted with kind of the obscurity of the results coming out of the big accelerator projects. And I guess one of the things that I'm wondering about is from a next generation transportation perspective, it doesn't seem like quantum mechanics is going in the right direction to really ever produce results. Do you think that there's room for growth left in quantum mechanics in terms of applied science? And do you think...
Well, when you're talking about these accelerator experiments, they're not just quantum mechanics. They're more than that. Bose-Einstein condensation, that's basically quantum mechanics. But these accelerator experiments are telling you a whole lot more. As we said, these accelerator experiments might tell us about the existence of extra dimensions if we're lucky. And so that's another thing that I really try hard to get across in my book, Warp Passages, is exactly how these accelerators tell us things, what they tell us, why they're interesting. What are the new things about the world that we might learn? And they're really quite exciting. And I also sort of start each chapter with little stories, and they're sort of joking. But one of the things that I'm doing a little bit is tying in the idea that as we understand technology more, we have better transportation communication, but we also have better physics. And the connections are often indirect, but they exist. I mean, after all, the World Wide Web came about because of CERN, the accelerator that's located in Geneva, this accelerator center. Basically, you had these international collaborations of physicists, and they wanted to be able to communicate. And so that's how the World Wide Web started. So sometimes what comes out of it is surprising. It's not even necessarily directly connected to the physical results you find. But certainly by learning more, we have a better chance. And even if it doesn't have practical applications, how could you not be interested in knowing the fact that we live in extra dimensions?
Oh, absolutely. Well, and it sounds like, unlike kind of that maybe somewhat clear cutoff between relativity and quantum mechanics, it sounds like it's more of a blurred model then. It's not going to go just from QM to string or brane theory. It's going to be more of a blurring between the two, right?
Well, I wouldn't call it blurring. I would say that, you can call them different fields of physics, but, I mean, Einstein, for one, knew that all physics should be connected. That's why he could work on so many different things at the same time. It's not like we just live where quantum mechanics applies. It might be that certain regimes, quantum mechanics is more important. But when you do particle physics, both quantum mechanics and special relativity play a role. You don't necessarily need general relativity, but you do need special relativity. At very high energies, general relativity would play a role. But at the kind of energies we see, I mean, it could be elements of string theory play a role. It could be stuff that we're building from the bottom up based on principles we understand already. We don't know, but it's not that they're blurring. It's that they're really combining together. We're putting all the ingredients together and seeing what we could find.
Ah. Well, we've touched on torsion and teleparallelism a little bit in a previous question, but one of the concepts that may be sort of related to this is the concept of quantum teleportation. Now, nobody these days seems to question the idea of non-locality in quantum mechanics, and teleporting quantum states across a lab is now a tested phenomena. What interests me isn't why teleportation and non-locality are so entrenched in quantum mechanics, but why more physicists aren't trying to find really large-scale parallels to these ideas in other models. Do you think that brane theory will ever hold a parallel concept for some of this quantum weirdness that we're used to in the QM model?
Well, the question is how interesting a phenomenon you can get out of it. I mean, for example, one thing we have are things called orbifolds. In orbifolds, you sort of identify points across a line. So in that sense, you might say, well, what's happening on one side is related to what's happening on the other. But you don't have to think of it that way. You can just think of it as a boundary. From our perspective as physicists, we're not really getting new phenomena out of that necessarily. So we're really interested in finding when do we get new phenomena. Certainly, a lot of people think that if we understand gravity better, quantum gravity better, we will have to understand non-local effects better. But on the scales that we see, we don't really deal with non-local phenomena. Interactions so far look local. If we could see or understand non-local effects, we would love that. We're trying to see could that play a role. But so far, local quantum field theory has been very successful. Predictions work really well. So you can just try to throw it in, but then you have to say, why does everything else look the way it does?
Absolutely. Well, I guess we're almost out of time, but I'd like to wrap things up with kind of an interesting conceptual question. Mainstream physics really seems to hate the word ether because it conjures up visions of the planets floating in a giant ocean filled with sea monsters and mermaids. Now, there's been a lot of fighting about this in the physics community. I think a lot of confusion as well because a lot of our contemporary models use concepts like quantum foam and curvature of time-space and the Dirac sea, which almost seem to me like kind of yet another concept of the ether. Do you think our current models are really ether theories? And does arguing about the terms and the semantics prevent serious research into manipulating these that might otherwise occur?
So the three things that you mentioned, they're really all very different. Quantum foam is something we're only just beginning to understand. Could we have extra universes once we get up to quantum gravity scales? Dirac sea is something we understand really well. We understand how antiparticles play a role, and we understand how particles play a role. We really do understand that. So there are some things we don't understand. We understand space-time curvature extremely well, as long as we don't get curvature on the scale of quantum gravity, that is to say 10 to the minus 33 centimeters. So there are phenomena we understand, there are phenomena we don't. So when physicists say ether, they talk about the theory that Einstein essentially debunked, that had to do with how electromagnetism traveled. And so that's the notion that people throw away. There are other kinds of ideas which we would call them fields. If we have things that exist throughout space, we're perfectly happy to consider fields. And in fact, if interactions are local, we need fields because we can only influence something nearby. And so somehow it has to travel, and usually it's by a disturbance that we encode in a field. So we just don't use the word ether very often. Occasionally people will use it half-jokingly. It's just a terminology question, but that, like I said, it's really this theory that got debunked. So we talk about fields instead.
Absolutely. Well, thanks again for your time. This has been a wonderful opportunity to share your insights and expertise with our audience. And I think that they'll be very excited to finally get some more knowledge into your work in string and brane theory. Again, your new book is entitled Warp Passages, and it's available at Barnes & Noble or Amazon. And again, I'd just like to say thank you. It's been a wonderful, wonderful opportunity to be able to interview you.
Well, thanks for having me here. This has been a lot of fun.